Oh no, man. Nemo's trapped. He got caught. Super bummed out. He happens to be in this fish tank, and because he's bummed out, all he's doing, he's spending his whole day just kind of swimming to one side. He'll hang out there for a few seconds, and then he'll swim to the other side, and he'll hang out, and that's all he's got, man. He's got to get out of that situation. But what we're going to do is we're going to analyze this. We're going to try to see how we can nail this down and describe Nemo's motion, at least for a brief period of time. So we're going to watch him. He's in this fish tank, and this fish tank is 50 centimeters from end to end. So that's how far he's swimming. He swims at a constant velocity to the other side. So he's starting here. That's his starting location. And so he swims to the other side at a constant velocity. It takes 6 seconds to get there. On the other end of the tank, he rests for 3 seconds. Then he turns around and he swims back at a constant velocity. And it takes him 6 seconds to get back. So over here, when he's hanging out over here, he's resting for 3 seconds, right? And there's 6 seconds to go from here to here, and then 6 seconds to go from here back to his starting point. So what's going on? We know at different times where he is. We're measuring time in seconds. We know position in centimeters. When we first start looking at his location, right here where we begin, no time has gone by, and he has moved zero centimeters. So you can kind of think of that initial location as the origin. That's kind of similar to an origin on a graph. 6 seconds he takes to go the other side. So 6 seconds later, he has a new position of 50 centimeters. Now there's something important here. You have to remember which way will be the positive direction, right? That is super important. So let's do this. Let's just identify for ourselves that to the right will be the positive direction. That's how I'm going to do my coordinate system in these situations. And you really, really need to keep that in mind. Now he's resting here at this new location, this new position of 50 centimeters. He's there for 3 more seconds. So after 9 seconds have gone by, where is he? He's still there. He'd spent 6 seconds moving and then 3 seconds standing still, resting. Then he turns around and goes back, and so it takes him 6 seconds to go back. So 9 plus 6 is 15 seconds have gone by. Where is he now? What is his new position? His new position, he's back at the origin. He's back at position 0. So that's Nemo's motion right now. And what we want to do is take that information, and we're going to create a PT graph, a position time graph. You knew that was coming, so let's do that. Got my handy dandy graph paper. I'm going to try to make a nice neat graph for you. I have in my graph paper plenty of room on these 2 margins, so that's not an issue. And I think what I want to do is I'll put time on the horizontal axis. Time is measured in seconds. And here's the positive direction for time. Not that that's really important. Now also I'm going to put position on the vertical axis. So this is something, position measured in centimeters. This is something that once in a while throws students off. So check this out. What was the Nemo's path? He went this way, and then he went back that way. On our graph, we're going to create this position scale going up and down, and that would be the positive direction there. And so, well, okay, it's kind of like this instead, right? If we're starting, here's the origin of the graph, well, here's the origin of Nemo's motion, and then he moves this way in a positive direction, so that's positive on my graph. And so our graph does match reality. We're just rotating things like this, because this is how we want to make our position time graphs. So what's the information we have to graph? We're going to look at the times and the positions. The times go up to 15 seconds. Well, I have a lot of space here, but I don't necessarily have to use all of it. What if I start here at time 0, and what if I go 1, 2, 3, 4, 5 seconds, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That looks pretty reasonable to me. I have a little bit of extra space that's unused, but it's not that big a deal. Position. I go from 0 to 50, and I'm up at 50 again, and then down at 0. In this space, I have to be able to fit a scale of 50 centimeters. Well, if I go by 10, so there's 10, 20, 30, 40, 50. 50 would be right there, counting by tens. Oh, that's really short. What if I extend that? And it looks like I have enough room to double that. So I'll go by 5s. There's 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Perfect. Right? No problem. And there's a position of 0. So this graph is pretty much set up and ready to go. Well, we should probably throw a title on it. Okay. And so now what? Well, we have data to plot, information to put onto the graph. And so, at time of 0, the position is 0. So 0, 0, right there. At time of 6 seconds, position of 50 centimeters. So there's 5 seconds, there's 6. I want to go up to 50 centimeters. At time of 9, I'm still at 50 centimeters. So there's 10, back up 1. I go to 9, I'm still at 50 centimeters. And now at time of 15, I'm at 0. I'm back down to 0 position. So there's 15 seconds, but position is 0. Okay. And there are plenty of times when you absolutely do not want to just connect the dots. But in this case, you know what? That's what we're going to do. Connect those. That. Okay. So remember, I'm sort of violating a rule about connecting the dots. Most of the time you will not want to do that. Okay. So now what about this graph though? It sure looks like there are 3 different sort of areas or 3 different zones or regions on this graph, yeah? There appears to be a region right here. I'll call it region number 1. There appears to be a region here, number 2, and a region here, number 3. And so these things mean something. So I'm going to keep that graph handy. Don't want to lose track of it. But now, those 3 different things, 3 different motions are taking place. Look, this cannot be the same motion as that, and that can't be the same motion as that. And look at this. Compare 1 to 3. That cannot be the same motion as that. So what's going on? Okay, we have a graph. These are 3 different line segments. Each one has a different slope to it, right? So that's what we're going to look at. In region number 1, what is the slope? How do we find the slope? Well, a slope is usually an m in math class, and that's going to be a change in y values divided by a change in x values. Okay. And a change in y values. So here's an explanation of that delta symbol, that triangle. Anytime you see that, what you say is change in something. So change in y or change in x. But when you want to find it, you have to take final minus initial values. So the final y value minus the initial y value. That gives you the change in the y values. Same thing with x. We have a final x value minus an initial x value. Well, what the heck are those values here in region 1? We got to figure this out. So can I use this data point and this data point? Well, so this goes along with breaking the rule of just connecting the dots. Those are the only two dots I have to understand this area, this region on my graph. So sure, I can go ahead and use them. So watch this. What am I changing in y values? The y values started at, here's my delta y. It started at 0 and went up to 50, but I have to do the final value first. So the final value is 50. Sure, I'm trying to stay consistent here. Final value is 50. The initial value started at 0, minus 0. Now I'm going to look at my x values. So there is my delta x. What is the final x value? It is 6 for this region. And I'm going to take away the initial x value. That was 0. And so I'm going to have 50 divided by 6. Handy dandy calculator. Did I do that right? 50 divided by 6. Okay. And so that's going to get me, according to my calculator, 8.3. I rounded off a little bit. Awesome. What the heck though? So this is kind of important. The y values have units to them. If this is the y-axis on my graph, the units on that axis are centimeters. So I need to actually have that in there. How about the x values? Well, the units on the x-axis are seconds. So 50 centimeters divided by 6 seconds. This becomes 8.3 centimeters per second. That's a distance divided by time. That sure sounds like a speed, doesn't it? So remember, the slope of a line on a PT graph gives you the velocity, right? Now I said velocity, not speed. And you'll see why. So let's look at region 2. And let's find the slope. Change in y divided by change in x. I really don't have to rewrite that again, do I? It's kind of the same thing. However, look at this. In region 2, what is my final y value? It's 50. What is my initial x value? It's 50. How much did it change in this region? It really didn't change. The y values did not change. How about the x values? Did they change? Well, the final value is 9. The initial value is 6. There was a change in x values. However, 0 divided by anything is just 0. Which makes sense. For 3 seconds, Nemo wasn't moving. He was resting. He had no velocity. 0 speed, right? Okay, very cool. So now how about region 3? I'm going to find the slope of region 3. Change in y divided by change in x. What's my change in y values for region 3? Well, I do final minus initial. So my final value excuse me. Pardon me. Final value in the vertical direction, well, that's a 0 on the vertical axis, way down here. 0, and then my initial value was a 50. So I have to do 0 minus 50. In the x direction, I have a final value of 15 and an initial of 10. Is that right? No, not 10. Initial value of 9. Okay, so I have to do my final, it's 15. Minus my initial is 9. And these are centimeters and those are seconds. So this is going to be, this is going to be a negative answer, isn't it? 50 divided by 6 centimeters per second. And I'm going to get the 8.3 all over again. But that negative absolutely matters, totally matters. Does the fact that this is sloped downward instead of sloping upward like region 1, does that matter? Yes. Happens to be the same value, 8.3 centimeters per second, 8.3 centimeters per second, but this one being in the negative direction. Ho-ho, yes, that matters. Think about it. Think about the physical situation, right? We had Nemo first traveling in the positive direction at 8.3 centimeters per second. Then he rested for 3 seconds. He had no speed. Then he turned around and was going 8.3 centimeters per second in the negative direction. Why do I know that's negative? Because I said to the right is our positive direction. That means anything to the left will be the negative direction. So what we have here is a great representation of the real physical situation. And that absolutely matters here. So, in our situation, moving right, that means we have this positive answer. In this case, over here for zone 2, he was resting. And here, moving left, we have that negative answer, right? So what about this business though? You know, I mean, it's kind of a divider there on the page. Well, there's a question of how fast he's going. You can answer the question with speed. When you hear how fast, that really does imply speed. So for zone 1, the speed, 8.3 centimeters per second. And I think you would agree with that. How about for zone 2? The speed was 0 centimeters per second. And for zone 3, come on paper, the speed was, oh, now wait a minute. How fast was Nemo going in zone 3? Do we need the negative sign? And the answer is no, we don't. When we're talking about speed, we're only talking about how fast. We don't care about what direction, right? Then the negative sign only indicates a direction. That's all we have going on here. To the right is positive, to the left is negative. And if we see a negative, that only gives us direction, but speed doesn't care about the direction. What does care is that velocity word. Velocity. What is the velocity in zone 1? What happens to be the 8.3 centimeters per second. What is the velocity in zone 2? That happens to be 0 centimeters per second. What is the velocity in zone 3? Now I need that negative. It's there. Negative 8.3 centimeters per second. And that really matters because velocity includes both speed and direction. You do care which direction it's going if you're talking about the velocity. It absolutely matters. You don't care which direction it's going if you're talking about the speed. So we drop the minus sign. It's almost like speed is equal to the absolute value of velocity, right? I mean, all we did for speed was we dropped the minus sign. Sort of like that. So that's an interesting thing, maybe help you remember it. This is really important to remember. And what else? I mean, we took some information about Nemo's motion, and just through observing what he was doing, and we graphed it. We created a position time graph, and that was this guy. And we saw a positive slope is a positive speed and a positive velocity. We saw zero slope being no speed and no velocity. And we saw a negative slope would give us a positive speed, but this would be a negative velocity. Right there, velocity in the negative direction. Cool. So got some good stuff off of position time graphs. That's all for now. Thanks for watching. I'll catch you next time.